I'm going to talk about balance factor, which is important for a self-balancing AVL tree, which is a binary search tree that's balanced. To be balanced, each node has to have a balance factor of 0 or -1. So the way you calculate it out is the height. So you noticed the root node has a right child, and so going in this direction like this on the right, from the right child, there's a height of 2. So on the right has a 2, and on the left child of the root node has a height of 2 all the way to the leaf node. So to balance the balance factor of the root node, it equals 0. But so that fits. The root node is balanced. Okay, and so whenever it's not balanced, you calculate the balance factor of each node so you can so you know where the balance needs to happen. So like for the 12 node, the balance factor is 0 minus 0, which is the right height minus the left height. It's the same as this one, 0 minus 0. So that's a 0 balance factor and a 0 balance factor. Now for the 15 node, it has a left child, so the height, and has no right child, so it'll be 0 height for the right child minus 1 for the height of the left child, which is equals -1, which it fits. This has a -1, and this is 1 minus 0 because the right child has a height of 1, left child there is none, so it has a balance factor of 1, so that fits. So everything's balanced in this one. So for an unbalanced one where you need a balance, you can see right away it's what we would call right heavy because there's a higher height on the right. So the root node has a right child, and you can see the path is 3. So the balance factor equals 3, which is the height of the right subtree of the root, and the left child has a height of 2. So the root node is balanced. But when you look at the 15 node, so this one is just like the one before, 1 minus 0, that's balanced. That's 1. This is 0 minus 0, it's balanced. 0. So the 15 node, the left child on the left side has it's a height of 2, so you go -2. There is no right child, so you go equals -2. So the 15 is not balanced. So the AVL tree would balance this out, and it's right heavy, and I'm going to talk about that in a second. So the 15 node would need to be balanced out. That's going to be the issue there, and you're going to have to write an algorithm to balance it. And it'll go through. Lots of people use recursion. I'm not going to, but you go and fix every node. So every node has to be balanced is the main thing, not just the root node. About the AVL self-balance search tree. So when it's built from the binary search tree, but the difference is it balances. So when you're adding nodes or removing nodes, there's different helper functions that are going to balance the tree. So they calculate the heights, And so, for example, if it got loaded up like this is going to have a -3 balance factor. This has a -2 balance factor. So this is going to be what we refer to as a right rotation, where, assuming D is the root, C C becomes the new root, D becomes the right child, and B and A um, is on the left as left children. So it has 2 left children and 2 right children. It's still a -1 balance factor, so it's left heavy, but it's balanced. You want to keep it within 1, 0, or 1. That's a right rotation. The left rotation is the opposite. It's right heavy because the balance factor of this node is right heavy because the balance factor is positive. So it's 2, so it's going to be a left rotation. And you can see now you have a 0 balance factor. And then I'm going to show the double rotation right then left. Now you can see that this has a balance factor of the node 5, say that's the root, has a balance factor of 2. But this node here also has a balance factor of -2. So 16 is left heavy. And the root node is right heavy above it. So you got to do a right rotation. And you can see right here around the 10 node. Do a left rotation. So this is ended up being a height of 2 and a height of 2. So this has a 0 balance factor. So this has a 0 balance factor. So and so the other one would be and basically you have like this. This is going to be our left and right. Excuse me, this is over here, or maybe you don't have anything over here. Just so this is all left children. So you're going to balance this out. You're going to balance it around this node, whatever node that is, and you'll look something like this. And you have to do it like an algorithm to it'd be like that. So it'd be do the left rotation. Do a right rotation around this, just the opposite way of this over here. So that'd be a double rotation left and right. So I'm keeping it real simple there, small, but you do that with each node, and it'll be like I said before, tends to be a recursive thing. I'm not going to use recursive, but that's the general idea of what the AVL the algorithm needs to do to balance out the tree. Keep the balance factor within 1, -1, or 0. So I'm going to talk about the implementation of the AVL tree. I'm going to talk about an AVL tree. I build this with using my binary search tree class. So it's class AVL, and it implements the comparable interface for generics. So it has to be compared to objects of the same type, which are just going to be integers. So in another tutorial, I talked about the binary search tree. So the difference between the difference is the AVL tree balances itself out. Okay, so and it's a binary search tree that self balances. So the first constructor is a default initialize an empty AVL tree, which is just like what the binary search tree does. This is the start tree. Second constructor initialize the AV tree with an array of elements, which we'll call start tree. There's a string representation, but I'll be using the other one to print it out. This one just checks if it's a valid AVL tree. So I use the stack abstract data structure. Um, so the first thing that's pushed onto the stack is the root, and the loop. Then there's a while loop that continues until the stack is empty. The top node is popped from the stack and cast to the AVL node. So it determines if the node is not null, checks the heights of the left and right children. And so, like I said before, it's calculating to see if it's balanced. The balance factor is 1, 0, or -1. Okay, so, and if there is no child, it's -1. So if the node has a parent, it checks if the node is correctly positioned as a left or right child. And if it has no parent, make sure that it's the only node without a parent is the root node. So the right and left children nodes are pushed onto the stack, and it's traversing down the tree. So it's going to do this with every child node because they might have child nodes. And so it's only going to return true if it goes through the entire tree and passes. So that's the is valid Boolean. It is valid AVL. So I have like a little example here. So 10, 5, and 15 initialize the stack. Root node right there, 10 is pushed onto the stack. And in the first iteration, node 10 is popped from the stack. There's a height check. Left height of node 5, assuming the height is 1. Right 15, assume it's 1. And so check if the height is correct. If it's not 2, return false because we assumed it was 1 to start with. If node 10 has no pair, it checks as if node 10 is the root, which it is. And then 10 and 5 are pushed onto the stack. 15 and 5 are pushed onto the stack next. And now it does that with those. Node 5 is popped from the stack. There's a height check. And it checks it as a parent. Node 5 has parent 10. And it sees as if it's correctly positioned to the left of 10. And then no values are pushed onto the stack because it has no children. So now node 15 is popped from the stack. And then it does the same type of checks. And then that ends the loop. The stack is now empty, so that ends the while loop right there while the stack is not empty. And then it'll get a valid AVL tree. So this is the add. This is a really important function for the AVL. A new node is created, AVL node, with the value that's in. If the tree is empty, the node is returned as root. So the new node becomes the root node. They initialize the current root and the parent to null. Then traverse the tree to find the correct position for the new node. So while current is not null, parent equals current. So it's going to start comparing the value to make sure it puts it in the right place and change the current to current.left, cast it to AVL node. If it's greater, it's going to go to the right subtree, left subtree is if it's less. If it's using the compared to function. So the new node is inserted to the left or right child of the parent node, depending on the value. And then they set the parent node to the, so you set the node as the child node, and then you set its parent to the parent. See, parent.left equals new node, parent.right equals new node, depending on which side, which child it is. And new node.parent equals parent. And then it calls the balance path function, which I'll go over in a second. And you probably have an idea of, based on my discussion earlier, of how it works. This remove just deletes a node with a specified value from the AVL tree. I remember well, I didn't say this, but I made this to where there's no duplicate values. So I just initialize. I did the same before. Initialize the root. Initialize the node. The initialize the root of the tree and get the parent equal to null, which is the root's parent is null, and then loop traverses the tree to find the node with a specified value, and then it does the same type of traversing. Goes down the right correct side of the tree. So if the node is not found with the value, is at most one child, the child replaces that node that's removed. So when that happens, if the child there's a system of checks. If the parent equals null, that means it's the root node. So you set the child to be the new root. If the node is the parent.left, the left parent child of the parent, update the parent's left link. Parent.left equals child, or you parent.right equals child. So if the child is not equal to null, update the child's parent link, child.parent equals parent. If the node has two children, you have to find the in order successor. It's the smallest value in the right subtree. And so you initialize successor to node.right, and successor parent equals node. And so while successor.left equals null, successor parent equals successor, and successor equals successor.left. And so then you're going to replace the node's value with the in-order successor's value. Node.value equals successor.value. And you update the parent link to the successor's child. If the parent successor parent.left equals successor, successor parent.left equals successor.right, successor.parent.right equals successor.right. Then you update the child's parent link. Then at the end you set the node to successor. And then you call balance path to the parent, and then return true that something's been removed. Balance path, this method traverses the path from the given node up to the root, updating the height and balancing each node along the way. Update height is another helper method, updates the height of the current node, and balances the current node. And so I went over that a little bit in PowerPoint slides. So it calls update height, and it calls balance, and the node equals node.parent, and while node does not equal null, So it goes all the way up to the root. So that's when the parent is null. This updates the height of the given node. Update height. This mount balances the given node if it's unbalanced. So it's using the balance factor of the right child to perform a left rotation on the node and return the balanced node. So you get the balance factor, and then you figure out which way to rotate, and then you call, then you rotate it right or you rotate it left, and then you return the node once it's balanced. It's going to do that for the entire tree. And this is just calculates the balance factor. And so you're using the height. So this calculates the left height. This is the right height. And then this is your returning. And this is rotate right, calls update and rotate left. And these perform the actual rotations. X equals y dot left. T2 equals is the right child. And then so the x becomes the new root and y becomes the right child of x. That's on a rotate right. Then you update the parent, x and y, update the heights, and return the new root. Similar. So it just does that with every node. It's opposite direction. So rotate left would be counterclockwise, rotate right would be clockwise around the node. And then this is how, I mean, those are the same functions for search tree. This is how you can do it. You cast it to AVL node, and there's also the in-order traversal. You just do a super dot in-order traversal, and those are in the binary search tree all the way around. So when you keep everything modular like that, there you can just you can use you can reuse those functions. You don't have to rewrite all the code, and you just use this and cast it. It's a lot quicker. Okay, so I'm going to test this AVL. Oh, I forgot to show. You also have to make a node class. It represents a node of a balanced binary search tree. Each node has a value, a reference to a parent node, and a height, which are all important in keeping the AVL tree balanced. The AVL node uses generics. It's just because it has to be comparable to other objects. It needs to be able to use the comparable interface. Inherits the properties and methods from the binary search tree node. This is the constructor. Initialize the parent node and height of node. And calls constructor of the binary search tree with the value. Okay, so next I'm going to test so that's AVL node class. I'm going to test the AVL class. So I call this the test AVL class. Just one quick test to add and remove. So I just created an AVL tree. Add these to it, and then print out what's added, and then I'll print out what it looks like. And remember, ads should be balanced, and then I'll remove, and then I'll see how it looks after removing. And do some additional tests. So compile it. There it is. Let's run it. So All right, so this is what I added. Let's see. So 10, 20, 30, 40, 50, then 25 was added at the end. 10, 20, 30, 40, 50, 25 was added at the end, but they put it in here, and you can see it's the binary, it correctly used the binary search tree algorithm. 10 is on the left, the right is 20. It's all left subtrees. Okay, so far it's okay. Then remove 40 and 50. So it should remove these two. It's going to make it a left heavy. So 40 and 50 are going to be deleted. So see, 40 and 50 are gone. And you can see how it rotated the tree. So it rotated it right. It looks like it's the left, but that's the right subtree 30. And then I added 35 and 45 and removed 10. So this is going to be removed. It's going to add 35 and 45 first, and then remove 10. See how I balanced it out.